Hello everyone, my name is Kumar, and in this video I'll be talking about the brain tumor classification project that we have undertaken. So let me tell you what basically we are doing. Basically there are two broad categories of brain tumors, malignant and benign, and there are three very commonly occurring malignant tumors: gliomas, meningiomas and pituitary adenomas. And the treatment and diagnosis of these three differs, and it is very difficult to distinguish between these three classes manually, and the manual process of MRI interpretation is also very time intensive. So we have tried our machine learning approaches to solve this problem. Okay, so let me show you how this works. Let me choose a file to see the results. Let me scroll and randomly choose one. Let me choose this one. Okay, and upload. So here is the image. Our dataset contains images from different planes. So this is one of the planes, and it is taking all the axes and all the planes. So it is a big dataset containing more than 3000 images and various planes. So in the output it says that the tumor type is glioma, and this is the image that we have uploaded, and this is the image obtained after thresholding. Thresholding basically removes uh, some parts of the image which are not necessary, dependent on the threshold that you have set. So it is a basic binary threshold that I have done here to just remove some uh, some uh, some points from here which had really low intensity. Other better thresholding techniques are also done in this project by my teammates. So this is just for simple visual interpretation of the brain tumor. Okay, and this is the tumor type, and these are the features that we have extracted from this image. So these features are very important in terms of uh, MRI images classification. And if you use any traditional machine learning models, you will need these features if you are doing uh, any machine learning interpretation on medical images. Okay, and you can read about this, and if you don't understand, just click on it and it will show what this this type of feature means and what it does and how it helps in determining the outcome. Okay, so for example, this you can see that the contrast is the difference between minimum and maximum pixel intensity, and here is the definition of energy, and you can read it all. Okay, so now let me show you in the output of any other image. Again, random scrolling, and let me take this one. Okay, so this is a different plane, and this type of tumor is pituitary, and it is also, if you just after thresholding, there is something you can see in the pituitary, near the pituitary gland there is some brightness, and these are the features, and that's all it is. And you should know that this is a different plane than the earlier one. And so what my point to convey here was, we are using images of all the planes. Okay, now let me talk about the model that we have implemented. We actually have implemented many different models, and my other team members have implemented traditional machine learning models, like they have used traditional approaches that were used to solve the MRI imaging problems, like ensemble classifiers and random forest and deep learning. Deep learning is used by me, and SVM and all others are used by them. So I have used PyTorch for this purpose, and let me walk you through my code. I have already run all the cells, so because it won't take time for you to see the output. So here I am just uh, uploading the data set, and while uploading sorry, I'm downloading the data set for my project, and before uploading I'm just using these pre-processing methods, and I have just applied scaling and standardization, and I have stacked it to make 3D because I'm using AlexNet for my transfer learning approach, and it needs a 3D representation, by the Dicom images were 2D for each plane, so we need to stack it to make a 3D representation. So that's what I did here. And one more thing is, what I did is converting Dicom to gray level. So Dicoms are basically 16-bit representation. Dicom images are represented in 16 bits, and normal images are represented in 8 bits. 8 bits. So that's why you have already, you most of the times you see that the pixel values range from 0 to 255, because 2 to the power 8 is 256, right? 0 to 255, it is the range. But in Dicom images it is a 16-bit representation, so it is not only lying between 0 to 255. But for our process, for applying the CV techniques and better output from AlexNet, we need images that are represented using 8-bit scale. So we just converted here into Unit 8, and then we did the scaling. So I'm loading the data, and there are three types of data we have. Uh, what I mean is, data is divided into three parts. The first one is training part, which contains 1500 images, testing is 644, and validation part contains 920 images. And both of these are actually used for training, and this is used for validation, which means this is the data that the model have not seen during training, and the test data actually it sees during training if you are implementing early stopping. So we have used early stopping. So we have also used train set. We have divided data into train set. Now I have just loaded the model, and I have made the gradients false because it is a pre-trained model, so you have to it is better if you make the gradients false if you want to um, apply your training afresh. And in transfer learning, you have the freedom to modify the last layers according to your needs and your classification problem or any such problem in general. And this is very important because this how many layers you choose and how many what functions you use are actually determining how much accurate your results will be. So this is the part of hyperparameter tuning, and we have used cross entropy loss and Adam optimizer. And now the training part, we have uh, trained for 100 epochs, but we are also using early stoppings, and then and all it doesn't go till actually 100. It stops at max 8 or 10. So on what basis does it stop? We have used epochs stop, which means that loss is uh, if your loss is getting decreased for a greater period of time, that means you are just making the model less accurate and you are making it more overfit. So that's why we use this early stopping. So we have used it, and this is the code for that. And whenever losses just becomes less than the epoch stops that we have said, we have set 5 epoch stops here, uh, and so this is the training result, and it went to 8 epochs. It starts from 0. So, and this is the testing that we are doing in the validation set, and this is the output. We had like 89% accuracy, and accuracy is not that very reliable measure of how good your model is. So we are just using precision scores, recall scores, and FN scores, and in all the results, if you see in the first class it is around 69 and 77%. So for the first class it is not that great, but in the second class and the third class you can see a result of 96%, and one is around 91%. So in most of the cases we have accuracy above 90% or 95%, so that is a very good result. And this is the confusion matrix. You see the most of the uh, classes are accurately labeled. Okay, so in terms of machine learning models and the previous works done in this field, we have compared our result with other uh, research papers, projects, and open projects, and we have seen that we have one of the best results and out there, and we are also trying to improve it continuously. Okay, so that's all I had to say. Thank you. Have a nice day.